History taught you that Vikings were warriors. It forgot to mention they were also chemists. The same craftsmen who drove the iron rivets into the hull of the Gokstad ship, a 9th century longship excavated by archaeologist Nikolai Nikolaisen in 1880 and documented in his 1882 publication Langskibet fra Gokstad ved Sandefjord, now held at the Viking Ship Museum in Oslo, were running a surface treatment on iron that the commercial rust prevention industry did not formally replicate in a laboratory setting until 1906. Those rivets spent 1,000 years in the ground. They came out with a black, hard, intact surface, not corroded down to flakes, not eaten through to nothing, intact, no laboratory, no power tools, no proprietary formula. What they had was oil, heat, and a precise understanding of what happens when the two meet at exactly the right moment, passed forward through generations of apprentices who were never allowed to forget the consequence of getting it wrong. A sword that rusted at sea did not fail an inspection. It failed its owner, permanently. The material cost to replicate what those craftsmen understood is about $2. The industry that replaced it generates over $22 billion a year in rust prevention products alone, a figure reported by Grand View Research in their 2022 Global Anti-Corrosion Coatings Market Analysis. There is one specific thing those Norse smiths did to the iron before it cooled that changed everything. It is not the material they used. The material is sitting in your kitchen right now. What comes next is the part the hardware store never needed you to ask about. Viking crews did not get to test their solutions in comfortable conditions. Every blade, every rivet, every iron fitting on those longships spent months at a time in salt spray, freezing rain, and open ocean air simultaneously. If the metal failed, the ship failed. If the ship failed, the crew died, not struggled, died. The techniques that survived that test are still physically present today. The iron rivets from the Gokstad ship are on display in Oslo right now. The iron fittings from the Skolderev ships, 5 vessels intentionally sunk around 1070 CE to block the Roskilde Fjord in Denmark, excavated and documented by Ole Crumlin Pedersen at the Viking Ship Museum in Roskilde, show the same black surface treatment on metal that sat underwater for nearly 1,000 years before it was recovered. Crumlin Pedersen documented the metallurgical analysis in Ships and Boats of the North, Volume 4, published in 2002. Conservator John Bill, in his 2013 report for the Museum of Cultural History in Oslo on the Oseberg ship's iron hardware, noted the presence of carbonized organic compounds bonded directly to the iron surface, not accidental contamination, deliberate treatment, repeated, consistent, and purposeful across every fitting on the vessel. They did not survive because someone later preserved them. They survived because the chemistry does not expire. The rust prevention industry did not fail to discover this. They discovered it and then sold you something more expensive instead. A Norse iron fitting cannot be invoiced. A spray can of proprietary rust converters sitting on a hardware shelf absolutely can. But here is the part the industry hoped you would never ask. Exactly how that bonding process worked at the forge, and why it still works in your backyard this afternoon. That answer is 60 seconds away. This is not a new idea. Janet Lang, in her 2004 paper Iron and Steel in the Viking Age, published in the journal Historical Metallurgy, the peer-reviewed journal of the Historical Metallurgy Society in the United Kingdom, documented organic residues recovered from Viking Age iron tools and weapons across multiple Scandinavian sites. The residues were consistent with drying oils, most likely linseed oil derived from flax. Flax cultivation in Viking Age, Scandinavia, is confirmed by botanical finds from the Hedeby settlement, excavated by archaeologist Herbert Jankuhn between 1930 and 1939, and documented in his 1956 publication Heithabu, Ein Handelsplatz der Wikingerzeit. Lang's analysis showed the oil had polymerized directly onto the iron surface. Polymerized means it hardened, the way a drop of superglue hardens into a solid when it cures, except the linseed oil was reacting directly with the iron, rather than just sitting on top. That is not an accident. That is a deliberate, repeatable process that worked the same way every time, because the physics required it to. Else Rosedal, in The Vikings published by Penguin in 1987, documents iron production in the Norse world as a skilled, systematic trade. Smiths trained for years, knowledge passed through direct apprenticeship. These were not experiments, they were proven procedures, carried out across generations of use in the harshest marine environment in the Northern Hemisphere. Then, one industry made that proven solution inconvenient. Not wrong, inconvenient. In the early 20th century, the industrial coatings and surface treatment industry, built on proprietary chemical formulas requiring licensed application, scheduled replacement, and continuous purchase, made it commercially necessary to route every household through a product cycle. The knowledge that Norse smiths had maintained for centuries, preserved in the iron itself, now recoverable from the artifact record at the Viking Ship Museum in Oslo and the National Museum of Denmark in Copenhagen, became worth less than a tin of branded rust primer you run out of by summer. You cannot sell a subscription to linseed oil. You can sell one to an aerosol rust inhibitor that empties by spring. That is the complete explanation. Nothing was banned, nothing was hidden. The billing cycle simply did not have room for free. What Norse smiths understood about iron and organic oil, and what you're about to build for $2, starts with one physical principle so simple it fits in a single sentence. The answer is coming right now. At its peak, the Norse trading network connected Newfoundland to Baghdad. Ibn Fadlan, an Arab diplomat who traveled with the Rus Vikings in 921 and 922 CE, documented their tools, their camps, and their metalwork in his eyewitness account, the Risala, preserved in manuscript at the Meshed Shrine Library in Iran and translated by historian Richard Fry in 2005. Every smith operating across that network treated their iron the same way, without a hardware store, without a coating supplier, without a replacement schedule. The average household today spends over $40 a year on rust prevention products for tools, garden equipment, and outdoor hardware, a figure that compounds every season and never stops. Norse smiths paid nothing. The chemistry they used has not changed by a single variable since the 9th century. It is in your kitchen right now, and almost nobody is using it. If that number stopped you, this channel exists for exactly that reason. Every week, we recover one more technique the industry assumed you would never find. Subscribe and hit the bell so you do not miss the next one. You've seen this your whole life and just never connected the dots. Cast iron, the pan your grandmother seasoned by rubbing it with oil and baking it at high heat. That black, hard, smooth surface is not paint. It is polymerized oil, carbon-bonded fat that has fused to the iron surface at a molecular level. It is chemically inert. It repels water. It does not flake or crack under normal use. And it lasts for generations without being replaced. That is exactly what a Norse smith was doing to a blade in 900 CE. Same process. Same chemistry, same result. Different tool, different era, identical physics. A wood-burning stovepipe treated this way does not rust through. A garden gate hinge treated this way does not seize up after one wet winter. The iron does not corrode because the oil layer denies rust what it needs to form. A direct path from water to bare metal. Rust is not a property of iron. It is a reaction. And a reaction requires contact to happen. Most people who try this get one step wrong. It is not the oil. It is what happens to the iron before the oil touches it. That single step is the difference between a coating that lasts 30 years and one that peels away in a wet autumn. Here is everything you need. Here is what you need. I want to be honest with you about every number. Raw linseed oil or boiled linseed oil, available at any hardware or paint store, often for under $6 for a large tin. You will use less than a tablespoon per treatment. The cost per piece works out to pennies. Boiled linseed oil cures faster. Raw linseed oil takes longer, but costs slightly less and produces the same result. A propane torch or a gas stove burner. Most people already own one of these. A clean rag or a small piece of natural fiber. Cotton works. Wool works. Do not use synthetic fabric. It melts at the temperatures you need. The iron or steel item you want to protect. A knife blade, a hinge, a gate latch, a garden tool head, any unpainted carbon steel or iron surface, that is genuinely it. No primer, no specialty chemical, no proprietary product, no subscription. Here's the one thing most people get wrong when they try this. They apply the oil cold. They brush linseed oil onto a room temperature piece of iron, let it sit overnight, and expect the same result that a Norse smith got at the forge. They do not get it. What they get is a sticky surface that collects dust and grit, takes weeks to only partially cure, and rubs off the first time it gets soaked in rain. That is the failure. And the failure is entirely about temperature. The Norse smiths who treated the iron fittings on the Skuldelev ships, documented by Crumlin Pedersen in that 2002 Ships and Boats of the North analysis, were not applying oil to cold metal. They were applying it to iron that had just left the forge. Iron that was still hot enough to polymerize the oil the instant it landed on the surface. That is the variable, not the oil, not the iron, the temperature at which the two meet. When linseed oil contacts iron above roughly 200 degrees Celsius, about the temperature of a pan that makes a water droplet vanish completely in under a second rather than sizzle and dance, the oil does not just coat the surface, it reacts with it. The fatty acids in the oil oxidize rapidly under heat. They cross-link. Think of cross-linking the way braided rope works. Individual fibers that slide past each other freely. But once braided together, they hold as a single unit. The oil molecules braid together at the molecular level under heat, and in doing so, they bond directly to the iron surface beneath them. They do not sit on top. They become part of the surface. Water cannot get under that layer, because there is no under. The two surfaces have fused into one. Cold oil just rests on the iron surface like a film of water on a countertop. Heat closes the gap between temporary and permanent. Here is how to do this. Take your iron or steel piece. If it already has rust on it, remove it first with steel wool or coarse sandpaper until you can see bare, clean metal. You do not need to make it perfect. You need to remove loose rust and get to solid metal underneath. Any active rust left beneath a new coating will keep reacting under it and push the coating off from below within a season. Heat the piece evenly with your propane torch or hold it over a gas burner. Move the heat slowly across the whole surface. You are looking for a specific temperature, and the test for it requires no equipment at all. Flick 1 drop of water from your fingertip onto the surface. If the drop takes longer than 2 seconds to disappear, the metal is not hot enough yet. If the drop explodes loudly and spatters, the metal is too hot. Let it cool for 30 seconds and test again. When the drop vanishes silently in under a second without spattering, you are in the right range. That is your window. That is the temperature at which the Norse smiths worked this process. Apply the linseed oil with your rag and a thin wipe. Thin is important here. Not a coat, not a brush-on layer. A wipe, the kind that leaves the surface looking almost dry immediately after you pull the rag away. The moment the oil contacts the hot metal, it will smoke slightly and darken. That small curl of smoke is the polymerization starting. That smell, slightly sharp and slightly nutty, is the organic compounds reacting with the surface of the iron. Now, the next step is the one most people skip. It is also the step that separated a Norse smith whose blade survived 20 years at sea from one whose tools pitted through in 2 winters. Stay with this. Let the first layer sit for about 30 seconds while the piece is still hot enough to keep reacting. The surface will darken, then apply a second thin wipe. Same lightness. Let it smoke again. Wait another 30 seconds. Apply a third and final thin wipe. 3 layers total, all thin, all on a hot surface, each one building on the one before it. Then set the piece down and let it cool completely on its own. Do not rush the cooling with water. Do not move it to a cold surface. Let the temperature fall slowly so the polymerization process continues down through the temperature range where the reaction is still active. This takes about 10 to 15 minutes for a small piece like a hinge or tool head. When it is fully cool, run your finger across the surface. It should feel the way the bottom of a well-seasoned cast iron pan feels. Smooth, slightly hard, no grease, no tackiness. If it feels greasy or sticky, you applied too much oil. Wipe the excess with a clean, dry cloth while the piece is still very slightly warm. The excess comes off cleanly. The bonded layer underneath does not move. Now hold the piece over a bowl or the sink and pour water directly across it. Watch what happens. Water on bare iron sits on the surface and begins to stain it within seconds. Water on a correctly treated piece sheets off immediately, the same way rain sheets off a waxed car hood. The surface does not hold the water. There's nothing for it to bond to. That is the test. That is the only test you need. Eye, hand, and a cup of water. Nothing else required. What you just built is one of dozens of Norse surface techniques this channel documents directly from the archaeological record. Every single one was replaced for the same reason. It cannot be invoiced. If that matters to you, subscribe. This is where that knowledge lives. One treated piece protects one piece. What a Norse settlement at Hedeby, which Jankun estimated housed between 1,000 and 1,500 people at its peak in the 10th century, based on the settlement density mapped across his excavations, did with this same process at full scale, is the part that changes how you think about the cost entirely. Every smith in that settlement applied the same organic treatment to every iron tool, every hinge, every blade, every agricultural implement that left the forge. Flax was grown locally. Linseed oil was pressed on site. The treatment cost the settlement nothing beyond the labor of applying it. No outside supplier, no seasonal reorder, no budget line. The result was a community whose iron lasted long enough to be passed from one generation to the next. Tools were not replaced annually. They were maintained and handed forward. The logic is not complicated. If your iron lasts 30 years instead of 5, you forge 1/6 as much over a lifetime. You use 1/6 the fuel, 1/6 the raw ore, 1/6 the hours at the forge. Multiplied across a settlement of 1,000 people, across a century of continuous practice, that is the difference between a community that exhausts its resources and one that compounds them. For a modern household, the shape of the math is identical. Treat your garden tools once in spring and once in late autumn. 2 tablespoons of linseed oil total. No rust through winter storage. No replacing the spade head because the socket corroded through. No buying a new trowel because the blade pitted out under the soil. The iron you own this year is still the iron you use in 10 years. No bills. No infrastructure, no asking anyone's permission. There is one condition where this works less well than the Hedeby records suggest. Norse smiths knew it and built a response into their practice. The answer to that condition is the last thing in this script. The treatment bonds most effectively to iron and low-carbon steel. High-alloy modern steels, stainless steel being the clearest example, have a chromium oxide layer on their surface by design. That layer prevents rust on its own, which is why stainless steel is sold as stainless. But that same layer prevents the linseed oil from reaching bare iron to react with it. Applying this process to stainless steel produces almost no lasting result. Norse smiths did not encounter this problem because stainless steel did not exist. Their iron was bloom iron, high carbon content, open grain structure at the micro level, exactly the kind of surface that linseed oil bonds to most completely. Modern carbon steel, cast iron, wrought iron, and the mild steel used in the vast majority of tools, hardware, garden equipment, and outdoor furniture responds to this treatment in exactly the same way that Norse bloom iron did at the forge. If your piece is stainless, this is not your solution. If it says stainless on the packaging, or if it never rusts on its own after sitting wet overnight, set it aside. Everything else in your shed is a candidate. One more thing to check before you start. If the iron has a heavy mill scale on it, the blue-black factory layer that forms on hot-rolled steel during manufacture, the linseed oil will bond to the scale rather than to the iron itself. That scale can lift, sand it off first, get to bare iron. 2 minutes with coarse sandpaper, then the process is identical. Norse smiths worked directly from the forge. Their iron never had mill scale. The solution for modern stock is one extra step taken before the heat. Then everything that follows is the same. The iron rivets from the Gokstad ship are still in Oslo. They are still intact. The black surface treatment Nicolai Nicolaisen found bonded to them in 1882 is still there today, not because of preservation efforts, not because of controlled storage conditions, because the chemistry was correct the first time and has required no correction since. The linseed oil is still linseed oil. The iron is still iron. The temperature is still temperature. What you treated today operates on the same physics. I do not know what brought you here. It does not matter. It works either way.